Take a moment, look around you. Observe the world that surrounds you, from the smallest trinket on your desk to the largest piece of furniture in the room. Everything seems solid, reliable, and predictable, doesn't it? A world governed by cause and effect, where objects behave as expected, thanks to the comforting embrace of classical physics. We've built our understanding of the universe on these principles for centuries. But what if I told you that this certainty, this feeling of control, is just an illusion? A carefully constructed facade that hides a much more bizarre and unpredictable reality. It's true, what we perceive as solid and stable is merely a large-scale approximation of a reality that operates under entirely different rules. A reality that's far stranger, far more mind-bending than our everyday experiences would suggest. Because when we delve into the tiniest scales, the universe transforms into a cosmic casino, a place of pure chance and infinite possibilities. Here, particles can exist in multiple places at once, a concept known as superposition, blurring the lines between what is real and what is potential. And these particles only choose a definite state, a single location when we observe them, when we try to measure them. It's as if the universe is shy, only revealing its true nature when it knows it's being watched. Welcome to the perplexing, fascinating, and often counterintuitive world of quantum mechanics. It's a realm so bizarre, so fundamentally different from our everyday experience, that even its founders, the brilliant minds who pioneered this field, often struggled to accept its implications and doubted its completeness. And yet, despite its strangeness, it's the most successful scientific theory ever devised, a testament to its accuracy and predictive power. It's the invisible engine powering everything from the smartphones in our pockets to the sophisticated medical scanners that allow us to peer inside the human body. This incredible journey into the quantum world all began with a seemingly simple problem, a puzzle that stumped the greatest minds of the time. It was known as the ultraviolet catastrophe, a paradox that threatened to unravel the very fabric of classical physics. The old theories predicted that hot objects like a glowing ember or the filament in a light bulb should emit an infinite amount of energy in the form of ultraviolet radiation, a clear contradiction of what we observe in the real world. This seemingly small discrepancy forced scientists to confront the limitations of Newton's clockwork universe, the idea that everything was predictable and deterministic. They had to abandon the notion of absolute certainty and embrace a cosmos built on the principles of probability and inherent uncertainty. So buckle up, prepare yourself for a wild ride. We're about to embark on a journey to meet the brilliant minds, the revolutionary thinkers, who dared to peek behind reality's curtain, challenging our fundamental assumptions about the nature of the universe. We'll discover how their seemingly strange and abstract ideas have not only reshaped our understanding of the cosmos, but also continue to shape our world in profound and unexpected ways. Because the universe, it turns out, is not just stranger than we can possibly imagine, it's stranger than we imagine. Our story starts at the dawn of a new era in 1900. The world was on the cusp of unprecedented change, with new technologies and ideas bubbling to the surface. Little did they know, the very fabric of reality was about to be questioned. It was a time when classical physics reigned supreme, but a nagging problem, the ultraviolet catastrophe, was keeping brilliant minds like Max Planck up at night. He was a respected figure, deeply entrenched in the established scientific community, yet he dared to challenge the status quo. In desperation, and almost as a mathematical convenience, Planck proposed a revolutionary idea: that energy isn't continuous, but comes in tiny indivisible packets, quanta, discrete units of energy. Imagine energy not as a smooth flowing river but like a staircase, not a ramp. You can only stand on specific steps, not in between. Initially, even Planck himself was skeptical. He thought it was just a mathematical trick, a temporary fix to a pressing problem. But this seemingly simple trick cracked the very foundation of classical physics, creating fissures in the established order. The implications were far-reaching and profound. Enter Albert Einstein, a young patent clerk with a mind that defied convention. During his miracle year of 1905, he took Planck's radical idea even further, pushing the boundaries of what was considered possible. He proposed that light itself isn't just a wave, but is also made of these discrete packets of energy, photons, particles of light. This meant that light, the very thing that illuminates our world, possessed a dual nature. It was both a wave, spreading out and interfering, and a particle, a discrete bundle of energy. This was a radical concept that shattered centuries of understanding, forcing scientists to rethink everything they thought they knew about the universe. On the quantum scale, the rules are different. Things can be in multiple states at once. For example, an electron exists as a wave of possibilities, a fuzzy cloud of potential locations, until you measure it, until you try to pinpoint its position. Then, and only then, it snaps into a single, definite reality, its wave function collapsing. It's as if the universe chooses a specific outcome only when we look, when we make an observation. Einstein's groundbreaking work unleashed a storm of new ideas and fierce debates within the scientific community, ultimately making even his own theory of relativity seem relatively tame in comparison to the strangeness of the quantum world. The quantum revolution had officially begun, and there was no turning back. The very concept of reality was being redefined, and the world would never perceive itself in the same way again. The comfortable, predictable world of certainty, governed by deterministic laws, was fading away, replaced by something far more mysterious. Probability, chance, and inherent uncertainty now ruled the quantum realm, dictating the behavior of the smallest particles. And the weirdness, the mind-bending implications of quantum mechanics, was truly just getting started. With Planck and Einstein's groundbreaking discoveries, the very fabric of classical physics began to unravel. Their work laid the foundation for a revolutionary new understanding of the universe. Inspired by these paradigm-shifting ideas, a new generation of physicists, brimming with curiosity and ambition, dove headfirst into the uncharted quantum territory. They sought to explore the mysteries that lay hidden within the atom. Among these pioneers was Niels Bohr, a brilliant Danish physicist who dared to challenge conventional wisdom. Bohr proposed a radical new model of the atom, suggesting that electrons don't orbit the nucleus in just any path, but instead occupy only specific, quantized orbits, like steps on a ladder. When an electron jumps from one orbit to another, it emits or absorbs energy in discrete packets, quantum leaps. This revolutionary idea elegantly explained why atoms are stable and don't simply collapse in on themselves, a problem that plagued earlier models. But the question remained, why only certain orbits? What dictated these specific energy levels? The universe, at its most fundamental level, seemed to be governed by arbitrary, invisible rules, defying classical intuition. Then came Werner Heisenberg, a young German physicist with a bold and innovative mind. He introduced the groundbreaking uncertainty principle, a cornerstone of quantum mechanics. This principle states that the more precisely you know a particle's position, the less you can know about its momentum, and vice versa. There's an inherent limit to how accurately we can simultaneously know these properties. This isn't simply a matter of having bad instruments or imperfect measurement techniques. It's not a limitation of our technology. It's a built-in fuzziness, an intrinsic uncertainty woven into the very fabric of the universe. Erwin Schrödinger, an Austrian physicist, offered yet another revolutionary perspective. He described particles not as tiny billiard balls, but as probability waves, spread out in space. According to Schrödinger, a particle exists as a cloud of possibilities, a superposition of states, until the moment it is measured. The act of observation, the very process of measurement, forces this wave function to collapse, solidifying the particle into a single, definite outcome. Bohr, Heisenberg, and Schrödinger together shattered the deterministic clockwork universe and replaced it with one governed by chance, probability, and inherent uncertainty. The quantum world is not just weird and counterintuitive, it's fundamentally unpredictable, challenging our deepest assumptions about reality. And despite its strangeness, it's the bedrock, the very foundation upon which everything that follows is built. Schrödinger, troubled by quantum weirdness, created a thought experiment to highlight its absurdity. Schrödinger's cat. Place a cat in a box with a quantum-triggered poison. Until you look, the cat is both alive and dead, a superposition. Only observation chooses the outcome. Your act of looking determines reality. Schrödinger meant this as a critique, but it became the ultimate symbol of quantum strangeness. The cat in the box perfectly illustrates superposition and the observer effect. At the quantum level, reality is a game of chance, and we're part of the game. The boundary between quantum and classical worlds remains mysterious. Schrödinger's cat is more than a paradox. It's a metaphor for the nature of reality. The universe doesn't reveal itself until we look. And sometimes what we find defies all common sense. For decades, quantum mechanics seemed abstract, but it's the engine of modern technology. Lasers work because electrons jump between quantum energy levels, releasing photons in perfect unison. Semiconductors, the brains of computers and smartphones, rely entirely on quantum rules. MRI machines read the quantum spin of protons in your body, creating detailed images without harmful radiation. Even GPS depends on quantum mechanics. Atomic clocks and satellites use quantum leaps to keep time, corrected by Einstein's relativity. Without quantum mechanics, there would be no information age, no medical imaging, no navigation. The technology that defines our lives is built on quantum strangeness. Every device you use is a testament to a century of mind-bending science. Quantum theory isn't just philosophy, it's practical magic. The quantum world powers the world you live in. Quantum mechanics built the modern world, and now it's building the future. Enter quantum computing instead of bits, 0 or 1. It uses qubits, which can be both at once, thanks to superposition. This allows quantum computers to process countless possibilities simultaneously, solving problems classical computers never could. With just a few hundred qubits, a quantum computer could outpace all the atoms in the universe in possible states. This could revolutionize medicine, material science, and logistics. Qubits can also be entangled, linked so that measuring one instantly affects the other, no matter the distance. This spooky action could lead to unhackable communication and ultra-sensitive sensors. Building these machines is a massive challenge, but the promise is immense. We're learning to compute with the very fabric of reality. The next technological revolution is quantum, and it's only just beginning. Despite its success, quantum mechanics is still shrouded in mystery. The measurement problem remains. Why does observation collapse probabilities into reality? What counts as an observer? Quantum entanglement links particles across the universe, seemingly defying the speed of light. Experiments confirm this spooky action is real. No hidden variables, just non-local connections. The biggest challenge uniting quantum mechanics with Einstein's general relativity. Each theory works perfectly in its domain, but together the math falls apart. Are we missing a deeper order, or is the universe truly random? Some theories, like many worlds, suggest every quantum event splits reality into parallel universes. Quantum mechanics works, but its meaning remains elusive. The universe keeps its deepest secrets well hidden. Quantum strangeness spills into philosophy, inspiring the simulation hypothesis. What if reality is a sophisticated computer simulation? The universe has a smallest unit, like pixels on a screen, and only renders details when observed, just like a video game. Philosopher Niels Bohr argues that if advanced civilizations run ancestor simulations, we're likely inside one. The observer effect could be the simulation's code rendering reality for us. There's no evidence for this, but it shows how quantum mechanics shatters old ideas of reality. Reality may be a web of information and relationships, not solid objects. The observer and the observed are inseparable. In the quantum world, we help write the story of the universe. We've journeyed from a nagging problem in 1900 to the edge of a quantum future. Quantum mechanics has rewritten our understanding of the cosmos, revealing a world built on probabilities and uncertainty. Its legacy powers our civilization, from chips to lasers to medical marvels. Now quantum computers, sensors, and communication promise to transform our world again. But its greatest gift is philosophical, a reminder of our limits and the wonder of the unknown. Quantum mechanics keeps the biggest questions open, about consciousness, the universe, and our place in it. A century later, it still challenges and inspires us. The next chapter of the quantum story is ours to write.